Hi all. First of all, thank you for watching this lecture. This lecture mainly focus to give an overview about IC design and also to give an idea about different or key job roles in this VLSI industry. The main agenda of this lecture is to give motivation to guys who wants to pursue a career in semiconductor industry and also to give some basic idea about the different domains in this industry. We'll also briefly touch upon the economics part of the IC design. And this presentation also will cover the basic idea about the IC design flow. And finally, we will also mm, give a brief introduction about the key job roles in this industry. What is an IC? An IC is a short form of integrated circuits. An IC is basically a semiconductor material like silicon or germanium on which electronic circuits being built or fabricated. In earlier days, the electronics devices were bulkier and heavy. The main reason was all these circuits were built on a PCB board, which contains components like resistors, capacitors, transistors, etc., being soldered on the PCB board. Nowadays, all the electronic devices are of very less weight and also very thin. Main reason is that all these circuits were replaced by IC, which can accommodate a lot of components in a very less space. Thus, the invention of IC was a huge turning point in the evolution of technology. Why we are using semiconductors? Are you curious on that? Why we are using semiconductors for building IC? As you are aware of, uh, the materials can be classified into three, right? Basically, conductors, insulators, and semiconductors. So you may also familiar with the energy band term. The conductors doesn't require any external energy to move from valence band to uh, the conduction band because it's already overlapped. Whereas in insulators, it's behave exactly opposite. Even though if we excite, it won't. The electrons cannot move from conduction band, the valence band to conduction band. The main peculiarity of the semiconductor is that we can give a small excitation on and thus we can able to move electrons from the valence band to conduction band. This property is very useful and this property because of this property only we can use to build transistors. Since transistors is the basic building block of all the devices, so semiconductor material is essentially uh, used for building ICs. So right now briefly touch upon how we build an IC. Okay, all ICs are being manufactured from a single crystalline structure called wafer, which looks like a mirror, and these wafers are slide out from a big crystalline structure as shown in this pic. These ICs are fabricated on these wafers as shown in this pic, and each segment of an IC is called die, and this will cut out eventually and go for packaging. So that's how we are getting an IC. So it's essentially it's fabricating on a wafer and we are slicing out each die from the wafer to get an IC. It's all it's all good to know where we begin the whole journey in order to appreciate where we actually stand now in this industry. And so I would like to highlight few key or major milestones in the growth of VLSI industry. So in 1947, John Bardeen and Walter Brattain were the first one to build a contact transistor in Bell Laboratories, which is made by Germanium Semiconductor. In 1949, William Shockley invented the first bipolar transistors. In 1958, Jack Kilby and Robert Noyce invented the first ever IC. So in this picture, on the left, it shows the first transistor. On the right, it shows the first IC, which is fabricated by the Texas Instruments. So Jack Kilby and Robert Noyce were part of the Texas Instruments, and though these guys are the one who built the first IC. First MOSFET was invented at Bell Laboratories by Duan Kang and John M. Martin in 1959-60 period. In 1961, the first commercial IC was built by Fairchild and Texas Instruments almost at the same time. In 1963, the CMOS technology was invented by Frank Wallace at Fairchild. Moore's law is an important law in IC design industry. So Moore's law is actually a prediction from a guy called Moore. He states that the number of transistors on a chip doubles every 2 years. And this is a motivation for the engineers to integrate more and more transistors on the IC. So there are debates over this whether we can still look upon uh, this Moore's law or not, but still it has a significance as it can be treated as a good reference point, and it also motivates the industry to think beyond uh, to overcome all these difficulties arise due to the increase in the transistor counts. So a graph shows actually how the integration of transistors happened over the years. On the y-axis, you can see the transistor count. On the x-axis, you can see the years, right? Years, and how the industry, different technology, it's scaling with respect to the transistor count per year. This evolutions chart indicates the evolve of VLSI industry. This chart shows how the VLSI industry grew from a 1 micrometer technology in 1985 to a 5 nanometer or 2 nanometer FinFET technology in a span of 35 years. Some of these nodes were commonly used like 180 nanometers and 110 nanometers, which is especially for the sensor based application where speed is not a criteria but accuracy is. And in 5 nanometer to nanometer technology is mostly a digital driven technology where the speed is mainly the selling point. As technology shrinks, the size reduces because actual the channel length of the device is reducing, and thus we can incorporate more circuits in an IC, and thus the speed also will increase. So if you see the 5 nanometer to nanometer technology is the main useful for the high performance computing, artificial intelligence applications. So if you see on the just below, just before that, you can see the application, mobile applications, and coming to the other nodes, we can see a lot of sensor or device applications in this area. So it's depend upon the application actually we choose which node is better. So the next important term what we need to understand as we move up towards lower technology is that what will be the cost of an IC. So these are the three major charts. Uh, if you can see that the first chart is basically between process node and wafer cost. As you see, the wafer cost is increasing as we move down to a lower move. I would say rather move up towards a lower technology nodes. And if you see the cell density also it's increasing, which means that there are more transistors are integrated on a lower space. So what will be the cell cost? Cell cost will be reducing because we are able to integrate more transistors on a lesser space as we scale up the towards the lower technology node, right? This chart shows how this cost of an IC related to different design aspect or different aspects of the IC design. So how much we are spending for different part of an IC development. So if you see in older technology, the amount of money spent with uh, uh, different aspects like validation software, physical design verification is very less. If we scales up towards lower technology, then we are spending more money on different domains as you see, right? And this is a chart which shows how we are spending with respect to different aspect of the design development as we scale up towards the lower technology node. This is a very classical slide which indicates the yield of an IC. So it's very important to know about the how the cost of an IC uh, affects and relates to the technology. So these are the basic equations. I'm not going into the detail of it. First, one must understand is that the yield is a major factor which determines the cost of an IC. And actually, the yield, as the technology scales, we can integrate more and more transistors or devices. We can build more ICs on wafer, so that actually relates to an increase in yield, and which is essentially it's better for an what you call for an IC in economic point of view. So if you go on the left, we can integrate only less devices in this IC, or on the right, we can integrate more devices in the IC, which is always better because your yield is better and you are more cost effective. Moving on to the IC fabrication side, IC fabrication is nothing but process of imprinting circuits on wafers, and it involves different stages of operations. And I'm not going to discuss each process in detail, but it involves a lot of process, chemical and mechanical process uh, called oxidation, diffusion, ion implantation, etching, photolithography, etc. So the bottom one shows a CMOS basic CMOS process, how the IC is fabricated on a wafer. So I'm just tells you what it actually means. So the basic building block of a uh, uh, process is transistors. So how these NMOS and PMOS transistors are made on a wafer is showing in this cross-section view. So we have P substrate, which is nothing but our silicon or germanium substrate. On that, we have N plus diffusion to N plus diffusion, which is acted as our drain and source terminal of the transistor. And we have the bulk connection. So on the p-type we have a p plus diffusion doped on it, and from that we will get the bulk connection. And between two we were adding a gate terminal, but gate terminal is on a oxide, is built on an oxide. So the potential on this, depend upon the potential applied on this, a channel will be created on between the drain and source, and thus we can control the current flow between the drain and source. So that's how we built a NMOS transistors, and the PMOS transistors are built in the same way, exactly opposite way. But before that, we will embedded a N well on it, because it's we have to integrate the P plus and P plus diffusions on it, and we cannot do it on directly on the P substrate. So we will have an N-well, built an N-well inside the P sub, and then we will diffuse P plus P plus, and thus we will get the drain and source terminals, and also the gate terminals will will applied in between uh, uh, there is an insulator and silicon oxide, right? So built to make the gate. So that's how we built a PMOS and NMOS transistors. And we will this way we are building millions of transistors, and we are connecting these gates, drain, source, extra by metal layers, and thus build a bigger circuit, right? So that's how we build a bigger circuit on an IC. Because and essentially it's fabricated like layers, right? So that's how we build an IC on a wafer. So another major concept of the IC is the to understand about the IC design flow. So I will go through each one quickly initially, and then come back and little bit explain about each one in detail. So the first one is the IC specification or system specifications, which involves the study of feasibility of the architecture, your dice estimation, size estimation, and functional of, aspect of the IC design. And all this analysis and feasibility part will be happening on the system spec. And then comes to the architecture. Once we have a system spec, we will define an architecture for that particular application, and then we start to model with some behavioral model or some like using MATLAB or Verilog. We use to build a system model to understand the basic aspect of the architecture, and then finally comes to the design aspect where we'll actually break down into smaller blocks and design each blocks, right? So then there comes the aspect of the logic and circuit design, where you have analog blocks. So we'll do analog design and simulation. The digital part will be then we will that involves digital design and simulation and overall system simulations and validation. Um, Digital synthesis, all these part involves in all these aspects. Uh, Together we can call it as like logic and circuit design part. The next one is the physical design, which actually converts the circuit design into a physical design aspect, or like we have. So the major part of this physical design is that there are not different concepts are either for planning, place and route, parasitic extraction. All these parts comes under the physical design. There are two we can we can consider as a two-part digital physical design flow and analog physical design flow. But analog design physical design flow you can term it as a layout design. And finally, the physical verifications and digital side, we have statics, timing analysis, ST analysis, lot of simulation to make sure your system is working fully. A lot of iterations, lot of competitions. We'll make sure that system is working in all these different modes of operation. And finally, we will type out and GDS will be sent to the fab to fabricate it. So GDS is nothing but a file, encrypted file, which involves all this information about the layers and of the layout. So complete chip level layout. So now we will look into each one little bit detail. So system specification, right? So before an project starts, or we need to understand about the system or that application. So there will be a set of requirements that needs to be hold true in all conditions, especially different voltages, different temperatures, etc. And in this stage, we will decide which technology to use also. So we need to understand a complete knowledge of the application. So what signals are coming, what signals are giving to the outside world, what are the protocols we used for the communication between the external world to uh, the IC. These all things will be decided in this stage of uh, design flow. And it's basically a compromise between the marketing requirements, technology, and the economic viability of the IC. So this is the whole uh, key aspects of the system specification part. This stage determines what are the key blocks we are using for the system and how they interact with each other and how they interact with each other at what time and what operations need to be carried out at what time. All these information will be uh, what you call decided in this level, and so we have more clarity on the specs of each block in this part of in this stage of IC design flow. And this basically relies on you will use the expertise and knowledge of a experienced system architect to uh, build this architecture level design. So, and also some modeling also help us to understand the design better. The outcome of this stage is to give a block level specification or like a top to down kind of approach, right? So we can determine what are the specs for the blocks which we are included in the system. Okay. Next comes the circuit design aspect, and there are basically you can consider it as a four major domains depend upon the application and what kind of circuit you are designing. So one is digital, analog, RF, and mixed signal. These are the major key domains in an design of an IC. So the circuit blocks involves basically connecting transistors into a smaller blocks, right? So the circuit block design involves uh, basically we are connecting the transistors and build these smaller blocks. These smaller blocks will integrate to become a larger blocks, and these larger blocks will integrate to become an IC. So that's how the design flow goes. A lot of simulation tools are being needed to extract all these electrical characteristics from each circuit, right? So all these aspect will come under the IC design, this part of the IC design flow. So now we'll get into the details, little bit details of each design aspect. So digital design. Uh, Digital design, this uses transistors. Basically, in digital design, we use transistors as switches and logic circuits. So the initial phase of the digital design is behavioral modeling, which uh, in which we describe the functionality of a circuit in a high-level language, which you can call it as a hardware description language, which can be Verilog, VHDL, etc. Uh, so and there are certain tools to do all these operations. So Verilog, Excel, and C Verilog model, Sim, MPSim extra are some of the tools we use to do the coding in this language. And right side, and we can see some basic examples of VHDL and Verilog. Essentially, both are very similar, but uh, what do you call the syntax aspect, there are certain difference also. So, and each has its own advantages and disadvantages, which I'm not going into the details of that one. And once you are interested in it, I will give you some key textbook references where you can understand all these concepts. So, and next part is the synthesis part, which converts all these uh, description or behavioral part into a gate level interface, because we can only the gate level things can be fabricated, right? It's what we are writing is a behavioral model, and the tool understands this and converts the synthesis. What it synthesis do, it's like this synthesis tools understand this behavioral language and converts into a gate level netlist. And but there are certain criterias we need to or constraints we need to consider while doing. So like extra the power, area, speed, extra, right? The tools, there are tools like synopsis tools we are using for this is okay. So that's about the digital design. So these are the key major references. So digital and logic computer design from Maurice Manu, digital circuits and logic design from Samuel Seeley, digital design from again from Maurice Manu and Michael D. Selby. These are the major or key uh, textbooks I would say to recommend. I would recommend for the digital design. Okay. So next comes the analog part. So what's the major difference between analog design and digital design is that analog is more like a personalized circuit design, and it deals with the signals which is continuous over time, right? That is essentially analog. The signals which vary continuously over time is called an analog signals, and in digital what we deals with only one sensors, whereas in analog we also interested in the all the time instance of a signal. So that essentially is an analog, right? But this also in analog blocks also we will start with the behavioral modeling to make sure like we understand the design better. So we use Verilog and system Verilog to model all these analog circuits. And compared to the digital design, we will not do a coding or we will not do an hardware language in this analog design. Basically, we draw the circuits by hand on a uh, software, right? On a software, like so in Cadence, uh, we have a schematic where we can draw all these circuits uh, like but actually it's like an hand drawing circuits and hand draw the circuits, all right. So there will be a lot of uh, devices or like basic building blocks available from our technology library. So like transistors, resistors, capacitors, diodes, all these things are available in technology in our what you call technology library, and we can instantiate all these technology libraries in the schematic, and we can depend upon the circuit performance. We can adjust the sizes of these transistors and connect each other to build a big circuit, right? So essentially in this example, I showed an inverter, right? So I instantiated PMOS and NMOS. I connected to the gate terminal together. I connected the drain and source of NMOS and PMOS and connect and taken out the output, right? So this is essentially how we can build a larger circuit also. So the tools which support this one is can Cadence, Synopsys, all these EDA tools which support uh, uh, this analog design. Okay. So the major uh, these are the key references of the analog design. If you're interested in analog design, you can go to the design and unlock CMOS integrated circuits or from Behzad Razavi, analysis and design of analog integrated circuits by Paul R. Gray, CMOS analog circuit design. Uh, yeah, all these circuits will be useful for understanding the basics of analog design. So next comes the RF design. RF design is nothing different from analog design. It's very similar. So only thing is that now we are dealing with an RF circuits rather than all the um, so the major difference is that it deals with RF circuits and signals. So that means you are working on the radio frequency signals and circuits which are associated with the radio frequencies. So the RF designs, the major difference is that there are different set of characterization that need to be carried out uh, compared to the analog design, because all the parameters what we are looking for the basics analog design is slightly different from the RF design. RF design we are more interested in other parameters like what do you call there are SPs, ZPs, some S parameter, set parameter, like you are worried about your third order harmonics, so P1 dB, IPP3, all these accept image or harmonics extra. So there are a set of characterizations which is already available in tools, but RF design require different set of characterization compared to a basic analog design characterization. So that's the major difference between RF design and analog design. But essentially, how the circuit we are drawing, we build on a tool will is very similar. It's almost very identical. The key takeaway from this thing, yeah, this is that only the characterization part is slightly different compared to the analog in RF design. So these are the major key reference textbooks for the RF design. So RF circuit design, RF design basics, RF microelectronics from Basil Razavi. So you can go through these textbooks and to understand about more about the RF design and concepts. So the next concept is mixed signal, which is nothing but new. It's an uh, what do you call it? It's a subset of analog and RF design because most of these nerve circuits require mixed signals where you need to integrate between analog circuits to digital, also from RF circuits to digital. So, so that area is commonly called as mixed signal design. And best example of a mixed signal design is ADCs. So ADC is nothing but, or DAC. So ADC is nothing but to convert analog to digital, and DAC is nothing but it will convert digital to analog. So both these interface circuits is essential for the interaction between analog and digital or RF circuit and digital. So this domain or this part of uh, the circuit design is termed as mixed signal design. So these are the major references of mixed signal circuits. If you want to understand more about the mixed signal circuit, especially the ADC, RF, RF plus digital, all these concepts, right? So you can go through all these textbooks. So next comes the physical design aspect of the IC design flow. This is a stage where the layout of the circuit being played out. That means this is the stage where your actual circuit is transformed into a layer of information of or a pictorial representation of layers, right? So this process starts with a floor plan. So before having the circuits, uh, before designing, before design itself, like when it comes to design phase itself, we start with a floor plan. So we need a floor plan like in how we build a house. So where the circuit sits and the placement of the circuits, uh, and then we will do the block level layout, so individual layout and how this interconnects, uh, and how we build a chip level layout. So we will should have a floor plan initially where all these blocks sits. Then we have to build the layout of each block. Then we have to interconnect each blocks to build a final chip layout. This also can be classified as two analog part and digital. So in digital terms, it called as physical. The physical design aspect of analog circuit is basically known as the analog layout. Analog layout is the manual process of laying out physical geometry of devices or components and connecting them together. So basically, on the right side, you can see a schematic of a inverter and how it is laid out in the layout. So basically, you can instantiate two transistors and MOS and PMOS from the technology library. So as a P cell, it will be already available mostly from the technology library. So that means you can get the NMOS and PMOS as already been built layout P cell. And then what we did
need to do is only connecting those gates together and drain and source of the NMOS and PMOS connect together and testing and also take the output. So basically, the same way we can implement all circuits, bigger circuits as well. So that's the main idea of being laying out. And there are tools which is used for having different checks in layout. Especially, example, the design tool check. There are certain rules associated with each technology, so we are not are we violating those or not? We can check using these tools like Caliber, Assure, and Hercules, and also in that we can check the design is uh, how the design is compared with schematic. So that is LVS layout versus schematic checks. Also, we can do using these tools, and also the PEX extraction. That means the parasitic extraction of this layout can also be done uh, by using these tools. And this actually extracted the netlist, which having the information about these parasitics also, and later we can simulate using these netlists and compare with the actual schematic and compare the performance of the circuit as well. Now comes the physical design aspect of a digital circuit compared to the analog circuit. The physical design in digital is a complete automated process. There are steps associated with different steps associated with physical design, that is partitioning for planning, placement of different blocks in the digital, like block tree synthesis to make sure your timing analysis are correct, signal routing, how the signals are routed between different the gates or circuits inside the digital, and timing closure. And there are a lot of tools associated with the digital physical design to make sure these steps are carried out effectively. And the timing analysis after the physical design digital is very important to make sure you are meeting all these timing constraints, timing uh, delay and timing and delays as compared to your schematic. So that's regarding the physical design aspect of digital circuit. Next comes the physical verification and sign-off tools. There are different design checks need to be carried out while doing the layout. That is design rule check, electrical rule check, layout versus schematic LVS checks, and also the extraction netlist. We have to simulate and make sure the schematic and the layout is matching with respect to performance as well. And there are other verifications such as UVM and AMS verifications, which is useful to capture RTL related bugs and coverage. That means in RTL there will be a lot of combinations which the circuit has to be work on, and using these verifications methodologies we can run a lot of combinations and regressions to make sure there is no bug, and if there is a bug it's very easy to capture at this level and fix it. And AMS verification is the one which deals with the interaction between analog and digital blocks and make sure your interface between analog and digital is quite clean and there is no surprises. So the verification is helpful for finding out the bugs earlier and fix those bugs before taping it out. So these are the basics verification strategy we need to follow while doing an IC design. And there are other certain checks verifications called IR drop, timing, and physical verification, physical design verification also to make sure your chip is working fine even after the layout, right? So because IR drop, there can be an IR drop if your routing is bad. There can be timing mismatch if your layout is bad. If there can be a physical uh, parasitic issue when we have laid out. So all these things we can capture at earlier and fix those things and move forward and to have a successful tape out. I already mentioned few times a term called tape out. What is tape out? A tape out is basically the final result of the design process of an integrated circuit. So before we are sending the files to the manufacturing uh, uh, or sending files for manufacturing, the tapeout is specifically the point at which the graphic information of the circuit is sent to a fabrication facility, and this the format at which the tapeout file is sending is called GDS2, which is a binary database which is encrypted and which contains all the information about the layout, including the layers, the properties, etc. So it contains the full, it's an encrypted file uh, which contains all the information of the layout, and this file is the one who we will send to the fab for fabricating uh, the IC. And this the fabrication facility receives this GDS file, and they run on their side to check all they will also do some checks to make sure there is no surprises in your GDS file format also. And if you have any issues, they will already also point out to the back to the team to make sure like there are some bugs we are seeing, and then we can there will be a time to make sure we can correct those and send it back. So, but the GDS2 is basically the final file what we send to the fabrication facility for actual tape out. So once the IC is fabricated, the next step is to do assembly and packaging. And assembly is the process of connecting uh, the I/O pads to the packaged pin using a bonfire. That is called assembly. And the step of uh, and encapsulating the IC in a case is called packaging. And there are different types of packaging here. There are dual inline packaging, QFN, where you have four sides, pins on four sides, and there are BGA where you have an array of pins on the bottom extra. And this is how it's connected the packaged pin to a IO pad using a bond wire, and which is and this die is encapsulated in a case, and this process of encapsulating this in a case is called packaging, and which gives the mechanical strength as well as it's also avoid wear and tear or getting impurities into the IC. So that's the basic purpose of IC packaging. And there are uh, the way the way we choose packaging also depend upon the application, and also sometimes the cost also matters to choose different packaging. Once we receive the IC, we have to test it. So there are two aspects of testing or verifying the IC. Uh, that is the manufactured IC. So IC validation is a process of testing the manufactured IC uh, for the functional correctness, or to check the functional correctness of the IC in a lab environment or a lab setup. That is called validation. And uh, IC testing, it's more like a product testing where it involved a lot of software and automated equipments called automated test equipments. There are different types of automated test equipments which will make sure the IC is gone through a lot of different aspect of uh, uh, combinations. That means there are different modes of operation. They will thoroughly uh, uh, make sure every aspect or every mode of operation is working properly, and thus we can successfully say that once you pass the product test, you can successfully give the IC for mass production. Otherwise it is not qualified for a mass production. So if there is a bug, you can we may there can be a software fix, or you may need to visit the design itself at sometimes. So in IC design testing, we can capture all the defects and uh, all the flows reliably. Whereas in IC validation, it's a very limited scope. So it's basically meant for only checking the correctness of the or functional correctness of the IC. Uh, that's all about the basics of IC design flow and the few concept of IC design. Now I will move into to give an overview about the IC job profiles in the IC industry. So the design engineer is the guy who is responsible for the design, chip design. It can be analog and digital. The layout engineer is the guy who is responsible for laying out the physical geometry of the circuit and do the verifications like LVS, DRC, and all these checks related to the layout. And application guy is the guy who's responsible to mimic the IC in the application environment. So to make sure the IC design wells in that environment. And verification engineer is the guy who is responsible for verifying the it can be digital design also the MS verification where you have to make sure your analog to digital phase are proper or there are in digital design research this verification guy will make sure there is no faults uh, by having a test bench and design those uh, digital blocks by giving certain test vectors and make sure everything is coming as intended. So that's the role of this verification engineer. Validation engineer is the guy who tests the IC in the lab environment, and test engineer is the guy who really like do the product testing in the automated environment. So, and this guy has to code, pre-program the firmware on the ATE, and then we can use the chip. We can use this ATE, and the chip can be integrated on this ATE, and then we can run a lot of test cases to make sure it's passing all the test cases. And CAD engineer is the guy who is responsible for all the EDA tools uh, and those stuffs were in the design flow we are dealing with a lot of software, so these guys will be responsible for handling these tools and to make sure we are giving the right parameters and the right accuracy settings for all these tools to make sure the design is proper. And till these are the mostly common job profiles in this industry. There are other lot of aspects like marketing team and other stuffs. Those who are not directly related to the design flow, but those guys are responsible for getting these things getting all these design into the market, and they will be communicating with the design engineer what market wants, and accordingly we will develop that product. And the cell characterization engineer is the guy who models the devices, and he will characterize the device based on a layout, and he will get information about or the characteristics of that extracted from those fabricated chip. They will do a fabrication of a sometimes a transistor alone, and they do characterize that transistor and get the behavior of the transistor and try to incorporate that behavior in the model so that we can effectively use that it for the design. So that's a basic role for the cell characterization engineer. Package engineer is responsible for packaging, and they have to undergone different aspects of it, the mechanical strength, how the bonding wire it should be, how the packaging should be, and all these, how the bond wire should be connected, how efficiently uh, the 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 resin sticks onto uh, the IC and all what kind of package we need to choose. All these things will be us responsible for the packaging engineer, and the product engineer is more like a responsible for all product whether it can be qualified for a production and whether we can successfully uh, give for a mass production, and then we can sell it to the customers. So all the qualification point of view of the product is responsible. The product engineer is responsible for those things. Next comes the VLSI company. I would like to classify VLSI companies basically into four. The product-based companies like ADI, PI, where they sell the products for a particular customer. They will do the products for different customers, but they have a particular requirement from a customer and they deliver that. And there are IP providers where give they will sell generic chips, and we can buy that chip and do whatever applications we can do. And there are product companies also also providing IPs, but there are companies which only delivering IPs also. And service-based companies are the ones who give service to a different company as a as a layout resource, as a design resource, as a verification resource, extra. So these companies don't do products as their own. They will do surveys for the other companies. And there are R&D companies who are meant for the research and development part. So there will be some investors, and they will be these R&D startup companies will be working on some ideas. And if they're successful, they can go for a mass production. And otherwise, it's obviously an R&D. So it's always a learning in R&D, and mostly there will not be time constraint that much in an R&D uh, uh, side, whereas in product companies there will be strict timeline to meet the deadline. And there are other R&D groups for the companies also, where they only meant for the research and development part, other than the product line. So there are different uh, portfolio for different companies as such. What companies look in a candidate while interviewing or not? It's all the basics. So if you're strong at your fundamentals of digital analog circuit and the basics of network theory, it is more than enough to crack any interview. Apart from that, your attitude, how he behaves, that all different matter. But technical point of view, uh, it's all about your fundamentals. So if you have a strong fundamental, it's very easy to crack VLSI interview. The people will look only mainly on your analytical skill and logical skill rather than you're answering a binary question like a yeah like yes or no or like true or false like that. So mostly they will ask for if you have done your masters, they will ask for your depend of your project, and they slowly build on that one. Or they can give into a basic RC circuit or draw an RC circuit and try to they will ask to analyze that one, and there can be different combinations. They will try to build on the basic circuit by adding some components and ask for like how that is behaving now, like how the circuit is behaving if we add one more cap, one more resistor, like that. They try to build on the initial question, and that's how normally the interview goes. So that if you have some basic if you have your basics clear and you are thorough on your basics, it's more than enough to crack most of the interviews. And the masters is the basic qualification, I would say, to get into a VLSI industry, especially as an analog designer or digital designer. And the internship is the best gateway to get into a VLSI industry, I would say, uh, because it will gives that will helpful for the company also to train them and acclimatize in their environment, so that it will be easy to understand what you are capable of, and then most likely they will hire you after your internship period. So that's how it normally works in VLSI industry. So keep calm and brush up your basics, and you are good to go
for any interview. That's all from my side. Thank you for listening this lecture. Hopefully you got some basic idea about VLSI industry and the key aspect of it. So thank you for listening. Once again, thanks and have a good day.